Good afternoon. Thank you for joining me. I am Mr. Ish. We are doing just a review video here on integrals, and this by no means represents the end of our integral topics because we still have other types of functions to go through. We're just doing review up to those types of functions we have looked at: trigonometric, basic polynomial, exponential, logarithmic. Whatever might show up over here is something we should be familiar with thus far. If anything new pops up out of the ordinary, we can always address it as it shows up. But I'm going to be looking at all the questions here, review questions here from my single variable calculus textbook. So everything here is from this textbook. Credit to the author is owed. Anyhow, let's look at these questions over here. So we are armed only with our intelligence, our motivation, and this reference sheet over here I have on the side in case I have to look it up. And we'll start looking at these questions quickly but efficiently. We have this and we have to integrate it, rewrite it in this format as you would now imagine to do so, like here. And integration of any polynomial with a minus will bring a natural log function. When you do the integration of this, u is equal to 5 minus 3x, du is equal to minus 3 dx, dx is equal to du over minus 3. See, du over minus 3. And we are looking at something which looks like u to the minus 1 du over minus 3, and you can bring this minus 1 over 3 outside and you still have u to the minus 1 du. So from over here, the next logical step is to bring in the natural log function because you have here to the power of minus 1. You remember that rule. You bring natural log and you put your u over here. You can put exactly what you see here, 5 minus 3x, and you can put a plus c over here. This could ideally be an absolute value and you would be good, but this answer over here would be the completion of this question, and it's an easy question, so we'll keep looking at more examples in this video. Alright, let's look at this one next. Composite over here. Let's do quick substitution. U is equal to e to the x. We know how to do it. Du is equal to e to the x dx, and dx is equal to du over e to the x. We come over here, we have e to the x, we have sine u, and then we have du over e to the x. The e to the x's cancel out and we are left with sine u du, which brings us to minus cosine u plus c. The integration of this leads to that, and then you are left with minus cosine e to the x plus c, and this right here would be our completed answer. The derivative of this antiderivative will give you back your original function and you would be good. How about this one? You have natural log in a parentheses affected by the exponent too, so you would look for this as being your substitutive item or substituent. U is equal to a natural log x, then du is equal to 1 over x dx, and you solve for dx. Remember, this is the substitution technique, is equal to x du. You substitute this and you substitute this in over here. This becomes u squared du, and you have an x. See, x du dux, you have this original over x. These x's cancel out. You're basically left with the u squared du, and when you do that integration, you get u3 over 3 plus c. When you resubstitute u for natural log x, you get natural log x all cube over 3 plus c, and this right here is your final answer. Easy question. Now this type of question is meant to throw you off. You have ax plus b in the denominator. You can bring it up, ax plus b to the power of minus 1 dx. You can do the substitution over here because it's a composite. U is equal to ax plus b, then du with regards to the derivative of x will just be a, because the b will be nullified because the derivative of a constant is a 0. Dx is equal to du over a, not hard. Then you come over here, you have u to the power of minus 1, and then you have du over a, but don't get confused by a. It's like it's not cancelling out with anything. It doesn't need to cancel out with anything. It was just a coefficient which you brought out. Nothing to be worried about with that, with this a over here. Now you do the natural log. You have 1 over a, the natural log of u plus c, because this leads to the integration procedure where you bring the natural log. You end up with 1 over a natural log of u. You can bring the absolute value because technically absolute value must come with a natural log, because you can't do a natural log of negatives. You can only do a natural log of a number larger than 0. And this right here is your final answer. Here is a good question. composite over here, we know substitution technique will play. U is equal to 1 plus e to the x. Then du is equal to the derivative of this. This is going to be a 0, and that'll just be e to the x. Some of these questions are just easy, but it's good practice. These are all from the textbook, as I was saying. You substitute this over here. You have e to the x, and then you have root u, and then du over e to the x. These e to the x's cancel out. You basically just end up having u to the 1 over 2 written this way is better rather than the radical. And now you have to do this is u to the 1 over 2 plus 1 over 1 over 2 plus 1, which is basically what? It's u to the 3 over 2 over 3 over 2, which is 2 over 3, and then u can be substituted for this 1 plus e to the x to the power of 3 over 2 plus c, and this right here is your final answer. From right here all the way here is your final answer. Now let's look over here. Integration of e to the power of cosine t multiplied by sine t dt. These t's could have very well have been x's. I'm looking over here right here for my composite. If I say u is equal to cosine t, then I say du is equal to minus sine t dt, and I solve for dt, which will be du or minus sine t. And you're going to substitute over here. You'll get e to the u, because our substitution was cosine t, so we get e to the u. Then you have sine t, and then du over minus sine t. These signs will cancel out. You essentially end up with this minus coming here on the side, and you're doing the integral of e to the u du, and you know the integral of e to the u will just be e to the u, because there's no coefficient over here which will come down in the denominator. You get minus e to the u plus c, but you got to resubstitute back the u. You'll get minus e to the cosine t plus c, and this right here will be your integral or your antiderivative of this question over here. This should not be a very difficult question. You know automatically you're homing in on this for your substitution. U is equal to tan x, and then du is equal to secant square x dx. And you know your substitutions are guided by the fact that you can try to come up with some substitution that will cancel your other item. It should always make your integral function easier, not harder, because things should cancel out. So you resubstitute back these two items over here. You have e to the u, and then you have secant square x, then du over secant square x. The secant square x is cancelled out, so you get left with e to the u du, a very similar question to the one before. And the integral of e to the u is just e to the u, and then plus c, because these are all indefinite integrals. Your final answer will be e to the tan x plus c, and you would be done. Not a hard question. Here is an interesting question because we have an inverse trigonometric function. Normally you don't see inverse trigonometric functions too frequently, but when you see them, you gotta grab them and use them. Look over here. This right here should not be your substitution, but rather this should be, because when you do the derivative of an inverse trigonometric function, you get a polynomial. Remember that. Remember the derivative of tan inverse x was 1 over 1 plus x squared. So you know you gotta do this as your substitution. So if u is equal to tan minus 1x, then du is equal to the derivative of this, which is 1 over 1 plus x squared dx, and you always solve for dx, is equal to 1 plus x squared multiplied here, 1 plus x squared du. Here's my substitution over here, and right over here. This inverse trigonometric function has popped up, so we gotta use it. And you would have u du multiplied by this 1 plus x squared, which you see right over here, divided by 1 plus x squared, which you see in the denominator here. These cancel out. You're essentially left with u and then a du, which integrates to what? U squared over 2 plus c. You gotta resubstitute u for this, which you get here as an arctan, or inverse tan, arctan, inverse tan, same thing, all square over 2 plus c. You see it was u squared, so it's this square over 2 plus c, and we are done. Seemingly was a difficult question, was actually easy. When you look at this question over here, you automatically home in on this composite in the numerator, and you make your substitution based on that. If u is equal to natural log x, then du is equal to 1 over x dx, because it makes sense to use a composite. You solve for dx is equal to x du, because this multiplied up here. And you come back where you do your substitution, you have sine u, and then du multiplying with the x, which is right over here, over the x, which is in the denominators. These cancel out. you end up with just sine u du, and when you do the integral of this, you get minus cosine u plus c, but you got to resubstitute back the u. You get a minus cosine natural log x plus c, and this question is completed. Here will be a tricky question. If you're doing the polynomial substitution technique, I would go for this right here on the bottom, and let's see how it plays out. If u is equal to 1 plus cosine square x, you have to do the derivative. Well, the 1 is going to come out as a 0, but you have to do the chain rule over here because you have a composite. You have d or du. If u is equal to cosine x, f of u is equal to u square. You have a u square over here. Du or dx, you can have cosine x, and then dx. You got to solve this out. What do you get? You get 2u minus sine x dx. And what do we get over here? We get 2, resubstitute back the u, which was a cosine x sine x dx. You have the minus sign, you can just bring it right over here on the other side. You can literally transfer this minus sign anywhere along this line. You have to solve for dx. Dx is equal to minus du over 2 cosine x sine x. See, here's our substitution over here, and here's our substitution over here to be done over here. But now before you do the substitution over here, use the trigonometric identity and expand this out. You know sine 2x is equal to 2 sine x cosine x over this u, which comes out over here. Bring this minus right outside as like a coefficient, and you have dx was equal to all of this. You will have du over 2 sine x cosine x. This 2 sine x cosine x cancels out with all of that. In essence, what you're left with is just a du over u and this minus outside, which you can rewrite as u to the power of minus 1 du. When you integrate anything with an expression to the minus 1, you have to bring the natural log of u, which was this 1 plus cosine square x here in absolute values, parentheses plus c. This right here represents the final answer to this. It was a seemingly difficult question, but when you worked it out using the trigonometric identity and using the right item for substitution, it was not too bad. Let's look at some definite integrals over here. Lower limit, upper limit, e and e to the 4. We have dx over x multiplied by the natural log of x in the square root. Our composite is over here. U is equal to natural log x, du is equal to 1 over x dx, and dx is equal to dux. But you gotta get the new intervals. u1 and u2. u1 and u2, these items here, the e values will be plugged in right over here. Natural log of e is just a 1, but natural log e to the 4 will just be a 4. You can run that through your calculator. The e's will cancel out, you'll be just left with a 4. You can see that with your calculator. You have a new limit of 1 to 4, and you have dux over x and u. If you do the substitution, this is what you get. Now you actually have to cancel out these x's. What you are left with is this lower limit, upper limit, du over u to the 1 over 2. See, root u is u to the 1 over 2. Bring the u up with the u to the minus 1 over 2 du, integrated. Minus 1 over 2 plus 1 divided by minus 1 over 2 plus 1. You have u to the 1 over 2 over 1 over 2. And you know you have a 4 and a 1. You don't need to resubstitute back anything because we're going to come up here with a final numerical answer as you do with definite integrals. Your antiderivative here is 2 root u and 4 and a 1. All you're doing is plugging a 4 in root u and then a 1 in root u, and you're minusing them. You're basically going to get 2 into 2 minus 1, and your final answer will be 2. You can do this mathematically yourself, and your final answer should be a 2. How about this lower limit, upper limit, x times e to the minus x square? Clearly you can tell this right here is the composite. We have to do u is equal to minus x square. You can do the substitution for this. Du is equal to minus 2x dx, and then dx is equal to du over minus 2x. We have to come up with a new bunch of interval values here, u1, u2, x1, x2, u1, u2. You plug them here, 0, x square, 0. 1 to the power minus x square is going to be a what? A minus 1. You're seeing that, right? 1 x square is just a 1, but it's still impacted by that minus. What you're ending up with really is minus 1 and 0. You see how we have a flip over here? We don't like the appearance of that. x e to the u du over minus 2x. Let's just cancel out this x and this x, and we can rewrite the minus 2 over here. We'll get a minus 1 over 2, 0, minus 1, e to the u du. Let's use the properties of integrals to flip this around by bringing a minus. You'll do a minus 1 over 2, and that enables you to flip the interval such that the larger number is the upper limit and the smaller number is the lower limit. E to the u du. Remember back to the properties of integrals, and this right here is a very legitimate technique. This minus sign allows you to flip this interval around. What you end up having is 1 over 2. Integral of e to the u is e to the u. You don't have to substitute back anything for u, but you have 0 and a minus 1. Solve it out. You have 1 over 2 e to the 0 minus e to the minus 1. We don't need to go for a numerical answer, but we can see what ends up over here. We have 1 over 2, e to the 0 is a 1, minus e to the minus 1 is minus 1 over e. You could numerically calculate all of this. You're basically having 1 over 2 times 1 minus 1 over e. We can do a fraction over here. We're basically ending up with 1 over 2 e minus 1 over e, and this can represent our numerical answer. You could have done a calculator answer for right over here and presented something, but I won't. But this right here is good. Let's focus here on this question. We have an inverse trigonometric function. We have 1 minus x squared in the root. You wouldn't think you should go for this, but we're trying to cancel things out, and this derivative of this inverse trigonometric or arc sine brings me something which looks like that. Think back to the derivatives. The derivative of sine minus 1x or arc sine minus 1x was what? It was equal to, if I remember correctly, 1 minus x squared. So our substitution should be based around this arc sine, the inverse sine. U is equal to the inverse sine. And then du is equal to this 1 over square root of 1 minus x squared dx. And then dx is equal to this multiplying up here. You have 1 minus x squared root du. And you come over here, you substitute u over square root of 1 minus x squared, and then du multiplied by this 1 minus x squared in root. These cancels out. You basically are just with u du. When you integrate this, you get u squared over 2 plus c. You got to resubstitute back u because it's indefinite integral here, which is your inverse sine. You have arc sine minus 1x square over 2 plus c, and that right here is your final answer. You could have written an arc sine x square over 2 or inverse sine minus 1x square over 2, and both are legitimate good answers. We haven't seen this so far, so let's do with this example over here, a hypothetical indefinite integral question. We have this 3x, we have 2 to the power of x squared. This right here is what the composite is represented by. And this right here is what you should use in terms of your substitution if u is equal to x squared. Remember, the substitution should be such that when you do the derivative of your substituent, it should help you cancel out the variable somewhere else in your function expression. You do du is equal to 2x dx, and then dx is equal to du over 2x. You come back over here. 3x, 2 to the power of u, du over 2x. This x cancels out with this x right here, and you end up with a 3 over 2 coming out as a coefficient of your integral. You have 2 to the power of u du. You know the integral of this is basically 2 to the power of u divided by natural log. You know, for anything which looks like this is going to be b to the power of x or natural log b, and that's the format you use over here. You have 3 over 2. Integral of this will be 2 to the power of u, which was x squared, over natural log 2 plus c. This right here is your antiderivative right over here. You can take the derivative of this and end back right at your original function, so let's just take the time and do it. This 3 over 2 can come out as a coefficient of your derivative process. And you have 2 to the power of x squared over natural log 2, and then natural log 2 can also come out as a coefficient. See, natural log 2 and 3 over 2, they've all come out. You're basically looking at this, which is a chain rule playing in over here. You have 3 over 2 natural log 2. I've just combined all of these coefficients into this 3 divided by 2 natural log 2. You'll have derivative with respect to u. You have a 2 to the u, and du with respect to dx. You'll have x squared. When you play all of this out, you have 3 over 2 natural log 2 multiplied by derivative of 2 to the u will be 2 to the u, which is x squared natural log 2. Derivative of this is always 2 to the u times natural log 2. Derivative of b to the x is always b to the x natural log b, if you're doing the derivative of something which looks like that. And the 2x will come out from the x squared, and we have a bunch of things to cancel out over here. This 2 will cancel out with this 2, this natural log 2 will cancel out with this natural log 2. In the end, you're left with 3 and the x, 3x, and then 2 to the power of x squared, which is your original function. See, original function right over here. So this question is completed. Let's look at one more such type of power function questions. We have this indefinite integral function to integrate, not hard. Composite here in the numerator, not a composite in the denominator. This root x should guide you into your substitution. If u is equal to root x, du is equal to 1 over 2 root x dx. You know, anything which looks like that always becomes that in terms of the derivative. Dx is equal to 2 du root x. You just took this entire denominator and you multiplied it up. Now you plug everything over here. You basically have b to the power of u, and then you have 2 du root x over 4 root x. This root x and this root x cancels out. This 2 cancels out with this 4 to give you a 2. Eventually you're left with b to the power of u over 2 du, and you can bring out the 2 as 1 over 2, as you know, it's in the denominator, b to the u du. When you do the integral of this, you eventually end up with this 1 over 2 b to the u, which is root x over natural log b plus c. Here our b just was a standalone variable with this exponent, but we had a variable instead of a number. It's all right. This right here represents our final answer right over here. You can do the derivative of this and you should end up back over there. And we can actually just attempt to do the derivative of this just for practice. These coefficients can come out 1 over 2 natural log b, and you're essentially just doing the derivative of b to the root x. That's all you're doing. Chain rule will come over here, 1 over 2 natural log b, d over du, b to the u, and then du over dx, root x. Okay, now let's play this out right over here. We'll have 1 over 2 natural log b, derivative of b to the u will be b to the u natural log b, but let's plug in the u back. B to the root x natural log b, derivative of root x will be 1 over 2 root x. Now we combine the terms and cancel out the terms which can be cancelled out. Natural log b can cancel out. 1 over 2 will multiply, and instead of putting our answer right over here, we'll come right over here for space and we'll do it. We have b to the root x on the top, b to the root x on the top, and in the denominator we have 4 root x. So this right over here, our intended answer is right over here. The derivative of this antiderivative has given us our original function, which you see right over here. So this right over here is a derivative process ending right over here. This right over here is our antiderivative of this original function. We'll keep continuing with this review video with more questions. You know, when we're doing the integration of natural log, it has that slightly chaotic form of a antiderivative. It's x natural log x minus x plus c, and that's the technique you have to use when you see something with natural log being applied with terms of the integration. You have to do a substitution technique because we have a composite. If u is equal to x squared plus 1, then derivative of either side, you're getting 2x dx, and then you're getting dx is equal to du over 2x, and this is indefinite integration, so it should be relatively easy. You're coming back over here, you're doing natural log of u, which represents as x squared plus 1, then you're doing du over 2x. The x's will cancel out. You'll have the 2 coming out on the side in the fractional form, and you're essentially now just doing the derivative of natural log, and you know what u represented was this. So you have to follow this with regards to that. You're going to get u ln u minus u, u ln u minus u over 2 plus c, but the u's have to be resubstituted back for x squared plus 1. You can use parentheses over here because otherwise it would look rather messy. You can do x squared plus 1 minus x squared plus 1 all over 2 plus c. We can put parentheses around all of these. This is very likely will be a positive term because you cannot create a negative term with an even exponent, so you don't need to worry about using absolute value brackets, you can stick with the circular parentheses, and this right here would be your final answer. For this function right here, natural log 3x, this 3x is a composite. Graphically, what are we really looking at? You know, in terms of the natural log function, it always goes through 1, 0, but here you can have a little bit of a shifting going on, a shifting that will arise as a result of this 3. Your x-intercept would be 1 over 3, 0, and you know what I did over here? 3 times 1 over 3 is a 1, gives you the natural log 1 with a y value of a 0. Your graph would look something like this. Away from this traditional 1, 0 intercept, you basically have the effect of this 3 creating a vertical stretch upwards, which shifts everything. So you end up having a new x-intercept. Anyhow, that's besides the point. We're still doing the integration of this. U is equal to 3x, and then du is equal to 3dx, and dx is equal to du over 3. Again, natural log antiderivative will be slightly convoluted. You're looking at natural log u du over 3, and essentially when you do this, you're going to get a 1 over 3. You get a u ln u minus u plus c, just like the previous question. There's nothing hard over here, nothing out of the ordinary. If this were a definite integral, you'd be trying to find some sort of area between a and b. Between this area, you'd be looking for some area, but we're not worrying about that. But that's how the question would have worded out as. Anyhow, let's complete this by resubstituting. You want to put a parentheses around all of this because this 1 over 3 is affecting everything over here. It's not just affecting this part, it's affecting everything. Your final answer will be, with the substitution of 3x natural log 3x minus 3x plus c. If you were to take the derivative of this antiderivative, you should very easily come back to that. Let's switch gears just a little bit. For this part, if you remember in the previous video when we were looking at the trigonometric integration questions, somewhere in the middle of that I broke away and I introduced 3 new integrals for you to know. Library integrals, in terms of there's a library of antiderivatives available. Based on that video, if you see something which looks like this, secant square x dx, you know you should automatically home in on this tan x plus c. Why? Because if you take the derivative of this antiderivative, you end up back over here. You know that. Anytime you see something which looks like this, you're thinking about that in terms of the antiderivative or the integral. If you see something which looks like secant x tan x dx, you know in terms of the antiderivative you should be automatically thinking about this, because if you do the derivative of this, you end up over here. Likewise, if you see something which looks like cosecant x cotangent x dx, if you see something like this, you should be thinking about minus cosecant x. In terms of the derivative of this antiderivative, you'd be coming back. Likewise, like these 3 similar scenarios, these are like one of those library of integrals we have. A situation such that when you see this, you should automatically be thinking this. There's another one of these types of functions you should be thinking of. Anytime you see anything which looks something like this, 1 over 1 plus x squared, and this x could be theta, and you'll have a d theta, or it could be a u, or you'll have a du, whatever the variable, it could have been a t, and you'll have a dt, but we're using x's over. Anytime you're seeing something like this, just like this, you should be thinking automatically of this antiderivative, because if you look at this antiderivative and you went backwards, you should be ending up with that, and that, if you have correctly imagined, is this. The inverse tangent, or you can say arc tan x plus c, because if you take the derivative of this, think back to the derivative of the inverse trigonometric functions. This went back to this in terms of the derivative. When I did the derivative of this in those examples, we were always getting 1 over 1 plus x squared. So anytime you see something like this, or one of those integration compound questions where you have something like this, you might as well be thinking about this. With regards to this, I want to show you why when you see this you should be thinking about this in terms of deriving it. And in terms of deriving it, now I'm going to very quickly give you a glimpse of another substitution technique, and that's called the trigonometric substitution technique of integrals. Right now, in terms of substitution questions I've presented, we've always been using the polynomial substitution. There's a specific technique called trigonometric substitution. I'm going to show you how this is this in terms of the specific trigonometric substitution technique. And that specific trigonometric substitution technique is something you should know, and it will be the topic of either the next or the video after the next, because that's a whole new video with a whole new different types of integrations you can start learning. using the trigonometric substitution technique. So what I'm telling you is this: if you see something which looks like dx over 1 plus x squared, because think about it, this dx is easily written as over here on the side with a 1 here on the top. If you see anything which looks like this, I'm telling you, in terms of the antiderivative, you should be thinking of this. Or you can say arc tan x. I'm saying you should be thinking about this, and here's why. You look over here, 1 plus x squared, just dissecting 1 plus x squared, you have a constant over here which we can call a. We have a variable over here which we can call x. And what you're seeing over here is something which looks like a squared plus x squared. Think about it. A squared here happens to be just 1 square, but you could have had a perfect square over here. You could have had a 4, you could have a 9, in which case a would be a 2 or it would be a 3. It could be a perfect square, but for the purposes of this process here, I'm just using a as 1. And if you think back to the trigonometric identity, the Pythagorean identity, you know something which looks like tan square x plus 1 is equal to secant square x. These x's can be replaced by u's, t's, thetas, whatever, the variables. But look over here, I want you to start thinking about something in terms of this, and I want you to start thinking about it in terms of this. Now look over here in terms of a square and x square, and look over here. You could have something which looks like the tan here represents a variable, x square plus a square. You're seeing something like that, aren't you, right? X square plus a square. Or you're seeing something which looks like x square plus 1, right? So anytime you see something like this, you should be thinking of something like this for the following reason. If a is equal to 1 and x is here equal to tan theta, let's bring in the tan theta. If a is equal to 1 and x is equal to tan theta, what you end up seeing over here basically is this. You end up seeing a square, or which is just 1 square plus tan square theta. That's what you're seeing, basically 1 square plus tan square theta. Alright, and this right here should equal to what? Secant square theta, right? 1 square plus tan square theta is equal to secant square theta. 1 square plus tan square theta is equal to secant square theta. So this right here is a trigonometric substitution technique, and it's going to play out like this before you, and I'm going to show it to you. Right now I've been only laying the foundation for that substitution technique. I haven't actually literally showed it to you. The technique is this. If x is tan theta, because we've understood that this looks something like this. If x is tan theta, then is equal to secant square theta d theta, right? du or dx, whatever. Here we're looking at x's, so we should be writing here dx. If x is equal to tan theta, dx is equal to secant square theta, and all you gotta do is substitute x for what you see over here and dx for what you see over here, and this is how it plays out. Dx is equal to secant square theta. You end up with secant square theta d theta on the top because you have a dx over here. This one is meaningless. On the bottom, what do you end up with? You have 1 square 1, it's all the same thing. 1 is same as 1 square. Plus x was equal to tan theta. You end up with tan square theta, because if x is tan theta, x square is tan square theta, right? You're converting this into this. And look over here, you rewrite everything in terms of the trigonometric identity I've presented to you over here. You end up with secant square theta over secant square theta d theta, which happens to cancel out, and you end up with just d theta over here. Right now I'm showing you exactly how we derive this. I'm showing you how you derive this from the appearance of this. Now let's create space over here, and we'll integrate this. We'll integrate this d theta. How do you integrate this? It's easy. Think back to it as being theta to the power of 0 d theta. You do theta 0 plus 1 over 0 plus 1. What do you get? Your final integration is just theta. This thing right here integrates to this. The antiderivative of this, the antiderivative of this right here. All of this is just theta. What was theta actually equal to? You come back right over here. X is equal to tan theta. Let's work over here. If x is equal to tan theta, you solve for theta. Theta, you take tan on the other side, you get tan minus 1 x, right? Which is the same thing as arc tan x is equal to theta. And this right here is indefinite integral theta plus c. So you essentially now substitute for any of these two, and you'll get that. Your final antiderivative for anything which looks like this is going to be, I'm just going to use arctan x plus c, and that's how you show that anything which has the appearance of this 1 over 1 plus x squared can be integrated into arctan x plus the constant of integration for indefinite example. So keep that in mind. Anytime you see anything which has this appearance in your question, and I'm going to be showing you 3 examples right after this of how this plays out, you should be thinking of this in terms of your antiderivative. Now look over here, x over 1 plus x to the 4th. If you made this unorthodox substitution, I'm saying it's unorthodox because normally I've been substituting the entire composites. If u is equal to x squared, du is equal to 2x dx, because you're doing the derivative of this, then dx is equal to du over 2x. Look over here, u was equal to x squared. You can rewrite all of this with regards to all of your substitutions, x over 1 plus u squared, because u squared, x squared will give you to x to the 4th. So 1 plus u squared very well with regards to this substitution gives you 1 plus x to the 4th. You still have the du over 2x. These x's can cancel out. Bring the 1 over 2 out, and now your final expression is 1 plus u squared. Like I said previously, it could have been 1 plus u squared, t squared, x squared, whatever. So long as it has the appearance of 1 over 1 plus some variable square, you can be thinking about that arctangent. When you see something automatically like this and you have to do the integration, you jump to that conclusion I've told you, that it's equal to tan to the minus 1x, or you can say arctan x. So the antiderivative of this, or the integration of this, or the integral of this will give you 1 over 2. Your answer will be arctan. But now look, here we're talking about x's, here we're seeing u, so you gotta say u plus c. You're seeing this, right? The 1 over 2 has come over here. This thing, based on the previous derivation process, is going to give you something which is an arctan, and I have that. But you have a u over here, you have to resubstitute back that u. Your final answer will be 1 over 2 arctan x squared plus c. If you take the derivative of this antiderivative, you'll end up back over here, and you can do that for yourself. You'd have to think back to the derivative of this, which basically gives you 1 over 1 plus x squared. When you do all of this with regards to this, right, you'll end up back to x over 1 plus x to the 4th. You'll see that, because when you do the derivative of this x squared, you'll get a 2x. The 2's will cancel out, you'll still get that x left, and that's how you get that x in the numerator. But anyhow, this right here is the antiderivative of this function over here using the procedures I've told you with this new integral that you've just learned. So look at this question right here, integral of sine x over 1 plus cosine square x dx. You want to somehow use this new technique you've learned and somehow visualize this in this form, and you can. You can do that because it kind of looks like a 1 divided by 1 plus x squared. You have to somehow visualize this in that form, and you can do that by means of a substitution which will eliminate that sine x on the top. Substitute for this. If u is equal to cosine x, then du is equal to minus sine x dx. dx is equal to minus du over sine x, and that'll help you achieve this into this form right over here. Look, bring the minus outside. You'll have a sine x divided by 1 plus u was a cosine x, so you have a u square, then a du over sine x. Once you cancel these things out, you get this minus du over 1 plus u square, and now you have somehow converted this into this form which mirrors that form. When you see this form over here, you can jump directly to this right here. You get a minus arctan, I'm just writing arctan, you could have written that, nothing wrong with that, arctan u plus c. You gotta substitute back for the u. Your final answer will be minus arctan cosine x plus c, or you can say minus tan inverse cosine x plus c. Either of these are good answers and they're final answers. So it would look like a difficult question, but by means of understanding that new integration process we've learned and a substitution, we've come back the right answer. For this question, everything falls perfectly within the template that we're trying to get, such that the integration of our function should give us some form of an antiderivative, which is the arctan. The only problem is this x over here. It spoils it. Otherwise we have a 1 divided by 1 plus x squared. We have to somehow deal with this extra variable we have over here, and the way you deal with it is to separate your integral by means of this positive sign. You can rewrite everything like this. you'll do 1 over 1 plus x squared dx. You see this 1 divided by all of this plus sign over here. Then you'll do x over 1 plus x squared dx. Now look over here. If you were to add these fractions, you have a common denominator, you'll still get 1 plus x and it'll still come back to that. But you've separated it such that now you've gotten exactly what you need. But look over here, these two parts will be handled slightly differently. You're going to handle this using the arctan integration process you've learned, which is a trigonometric substitution process really, but you'll be using this through a different process. Look over here, let's deal with this part right over here. If u is equal to, let's say 1 plus x squared, right, all of this substitute, then du is equal to 2x dx, and dx is equal to du over 2x. That's for this part right over here, the second part. Now what should we do about this? Well, we don't need to do anything about it because it already looks like exactly what we need it to look like for the arctan. So let's keep writing everything until we get to that step. 1 over 1 plus x squared dx, because this is a one-step process away from completion. And now this right here, x du over 2x, 1 plus u squared was u right over here. That's this part right here dealt with the substitution. Let's come over here. We'll still deal with this first part at the very end, 1 plus x squared dx. Let's improve this 1 over here. And over here, let's bring the x's and cancel them out. Let's bring the 2 out, 1 over 2. Let's bring the u up, u to the minus 1 du. You know you have the natural log kicking in over here. Now let's take this to completion. This one right over here is just arc tan x, and that part is done. Because this right here, when you see this, you're thinking about this in terms of your antiderivative, because when you go backwards in terms of derivative, you end up with that. But look over here, you can get 1 over 2, the integration of this is natural log u. But what's u? 1 plus x squared, right? 1 plus x squared. But look, because we have a 1 plus x squared, it's impossible to bring a minus in here, because any values over here will always be positive. You can just keep a circular parentheses plus c. This right here represents our antiderivative of this, and the question is done. If you were to take the derivative of all of this, you should end up with exactly that, and you can try that on your own, but this right here is a good answer. But you can see how we have to separate this into this across this positive sign here in the top. We basically did this. We took this and we separated it out this way, then we took this and we separated it out that way, and we separated it out exactly as you see it. We had to do this using basic substitution technique, and this we used the new integral we've learned in terms of the antiderivative, and we've come up at the correct final answer. Let's rewind our gears a little bit and just look at a quick review of questions for some basic polynomial substitution techniques. Look over here, here's the composite here, and the numerator it isn't. We'll substitute for this. If u is equal to x squared plus 4x, then du is equal to 2x plus 4 dx, and dx is equal to du over 2x plus 4. You will substitute it right over here, and you will see you'll have x plus 2, and then you have du over 2x plus 4. Over here you have a root u. Now look over here, this 2x plus 4, it can be factored is what I mean, isolated. Look over here, x plus 2 over root u du over 2 into x plus 2, because you can factor out a 2 from here. Now you suddenly have things which cancel out. This 2 can come out, 1 over 2, bring this root u up with the negative exponent du. You essentially have this left which has to be integrated, which is not hard. You get 1 over 2, u to the minus 1 over 2 plus 1 divided by minus 1 over 2 plus 1, you get u to the 1 over 2 over 1 over 2 plus c. When you finalize all of this, you'll get 2 over 2, which will cancel out. You'll essentially just get left with root u, which will be x squared plus 4x plus c, and this right here will be your final answer. How about this one over here? Cosine x divided by square root of 1 plus sine x. Composite here, substitute for that. U is equal to 1 plus sine x. Then du is equal to cosine x dx. Dx is equal to du over cosine x. Here's my substitution right here, and here's the other one. Bring it over here. You have cosine x over root of u, and then du over cosine x. We've seen questions like this too frequently now. we have du over u to the 1 over 2. We can bring the u up with a minus exponent du. You just integrate this, you basically get u to the 1 over 2 over 1 over 2 plus c. Bring everything to a clean finish. 2 will come up, you'll end up with root of u, which is 1 plus sine x. And here will be your final answer, your antiderivative of this function right here. If you take the derivative of this, you should end up with that. This question here will be slightly bit more involved, but you know you can go for this in terms of your substitution. U is equal to x squared plus 1, and then du is equal to 2x dx, and dx is equal to du over 2x. That's what we have so far. We have to bring it right over here. We have x cubed over root u, and then du over 2x. These x's can cancel out such that when you do the cancellation, you end up with x squared. This 2 can come out, 1 over 2, and you have x squared over root u du. Now look over here, we still have an x squared, x variable, and we have a u variable. The substitution should be such that when you're done and you're ready to do your final step or integration step, you should only have one variable. But we still have two variables, an x and a u. You have to come back over here to guide you as to how you would do this. You have to somehow get rid of x squared. If u is equal to x squared plus 1, then x squared is equal to u minus 1. See, x squared is equal to u minus 1, and you substitute that over here. You have 1 over 2 integral x squared is equal to u minus 1 over root u du. Now separate these across this minus sign. Look over here, 1 over 2, right there, u over root u du minus, and let's separate it out across this minus sign right here. And we have just a 1 over root u du. I've separated these under denominators, u under root u separately under each denominator, and minus 1 over root u. And you see that 1 over 2 affects everything over there. You can't forget about this 1 over 2 because it equally impacts everything. Now look over here, we write everything in terms of easier to understand denominators. Actually, we may not even have to do that. Look over here, u divided by root u is just u to the 1 over 2. That's just basic laws of exponents. Now over here, 1 divided by root u, you can just write that as u to the minus 1 over 2 du. Now you just have to do the final integration step over here, or n plus 1 divided by n plus 1. Remember the basic integration technique for polynomials? Well, that's what we're doing over here. 1 over 2 u to the 1 over 2 plus 1 is a 3 over 2, and you'll have a 3 over 2 here on the bottom, minus 1 over 2 times here, minus 1 over 2 plus 1 is a 1 over 2. 1 over 2 and 1 over 2. We'll write our final answer over here with all the substitutions and by handling the fractions as well. If 3 over 2 flips, you get 2 over 6, which is really a 1 over 3. You get a 1 over 3, and you can see that yourself. You'll have u to the power of 3 over 2. U was x squared plus 1. X squared plus 1 to the power of 3 over 2 minus this 1 over 2 will flip, you'll have a 2 over 2, which is just a 1. You'll just end up with the root u, which will be x squared plus 1 to the power of 1 over 2 plus c. Here's your final answer. 1 over 3 x squared plus 1 to the power of 3 over 2 minus x squared plus 1 to the power of 1 over 2 plus c. If you take the derivative of this entire antiderivative, you'll end up back to your original function, which will be right over here. And this question is done. We'll end this review video with these two last examples. We just do a quick 2 additional questions and that'll be it. Very quickly over here, we're doing the integration of 10x multiplied by 2 to the power of x squared minus 1. You know the common theme over here has been just a review. Simple review involving polynomial substitution techniques. Substitute for this x squared minus 1. If u is equal to x squared minus 1, because here this represents the composite we're looking at, du is equal to 2x dx, and then dx is equal to du over 2x. You have your two substitutions which will come right over here. You have 10x, 2 to the power of u, and you have du divided by 2x. This 10x and 2x can cancel out such that you can end up with a 5 right out here. So you end up with a 5 and the integral sign 2 to the power of u du, and you know a simple integration of this will lead you to 5 times 2 to the power of u over natural log 2. You can write this in a better way. You can do 5 divided by natural log 2, and then you'll have 2 to the u, which is x squared minus 1 plus c. And this right here will represent your antiderivative of this original function. We can take a quick derivative of this to make sure we're actually on the right track over here. You don't have to, it's just a totally extra step. This entire 5 divided by natural log 2 can come out as a coefficient, and you're doing derivative over here. We're doing a derivative here of this composite function. Let's bring in the u. If u is equal to x squared minus 1, f of u is equal to 2 to the power of u. And then derivative of u with respect to x, you have x squared minus 1. And then look over here, we have to do the derivative of this. We'll write everything else as we see it. Derivative of 2 to the power of u will be 2 to the power of u ln 2. Derivative of x squared is a 2x. Now we can cancel things out. Natural log 2 cancel out. 5 multiplied by 2x will give you 10x, right? 10x. We're trying to get back to the original function by taking the derivative of the antiderivative. You resubstitute back for 2 to the power of u, where u was equal to x squared minus 1, and we are exactly back to where we started. So this right here was our antiderivative, and this right here is back to our original function. Last question here, outrightly you can tell it's going to be an easy one, not too hard. Substitution here, u is equal to 3x plus 1 is equal to du over 3, because the derivative of 3x plus 1 is just a 3, and you bring it down over here, so dx is equal to du over 3. Substitute over here, you have cosecant of u, cotangent of u, and then du over 3. This over 3 can come out as a coefficient 1 over 3, and we're looking at basically this cosecant u, cotangent u, and when you're seeing this, it's like right there in your face telling you exactly what it is. That one new integral you learned not too long back ago, it would be minus cosecant u. The antiderivative of this minus cosecant u divided by 3, but we can resubstitute back u for 3x plus 1, and then plus c. So this right here is our answer, the antiderivative. You can take the derivative of this and end up back to where you were. It's not hard by any means. Take this 1 over 3 out as you normally would prior to any integration or derivation process or derivative process. Take out the coefficients, it makes things easy. You have a minus over here, take the minus out too. Nothing wrong with that. Now we look over here. We're doing a chain rule over here because we have a composite. So let's bring in the u over here. If u is equal to 3x plus 1, then f of u is equal to minus cosecant u over 3, which we have minus 1 over 3 right here. We can just write here cosecant u, and then we can do du over dx, 3x plus 1. We have a minus 1 over 3 coming out back inwards. Cosecant derivative is going to be minus cosecant u, cotangent u. Derivative of 3x is just a 3. The 3's will cancel out, the minuses will cancel out, such that in the end all you'll be left with is a positive cosecant u, cotangent u. But you can resubstitute back for the u's. You'll end up with cosecant 3x plus 1 multiplied by cotangent 3x plus 1, and that right here is your original function. Antiderivative derivation led to, or the derivative over here led to this. The derivative of your antiderivative gave you back your original function. And that is the conclusion of this video. It's a review video. Now you have to remember, up till now we've done basic polynomial substitution techniques. We have basically, if we want to be adventurous, we have to learn the trigonometric substitution technique. We have to learn how to do integration by parts. Once we can do those two new integration substitution form techniques, right, we'll be able to look at different types of questions. And that's when things will get more fun for us. So stay tuned for my videos as they're coming up. We'll be exploring slightly more difficult substitution techniques. And I have to, if you remember, I still have to present integration for other types of functions like hyperbolics, inverse trigonometrics, beyond just the arctangent we've learned. There's still other functions we have to learn how to do the integration for, and we still have to learn some substitution techniques. So stay tuned for all of that. Thank you for watching. Have a nice day. Bye.